Are there any questions? No? Let's go on with gas mixtures then. So if we have 1 liter of air, what can we say about what can we say about it? Well, 1 liter of air is going to have 80% by mole nitrogen, 20% by mole oxygen. Mole percentages. All right, tell me what else. What else can you say about this mixture? Describe this mixture to me. Could you say, could you say the mass percentage is this also? No. Because if you take 100 molecules, 80 of them will be nitrogen, 20 of them will be oxygen, but you know, the masses of the nitrogen and oxygens aren't the same. Mass of oxygen is 32, mass of nitrogen is 28 U, right, roughly. And so the mass, could you calculate the mass percentages? Yeah, it's not difficult. You get the mass of nitrogen, you assume, you know, you got to assume something, maybe 100 molecules. You get the mass of nitrogen, you figure out the mass of oxygen from 80 of those molecules being nitrogen, 20 being oxygen. You get the total mass, and then percentage would just be mass of nitrogen over total times 100%, etc. And so we could figure out the mass percentages without much difficulty, but what else can you tell me about this mixture? Okay, how about this? Can I ask you, is the pressure of the nitrogen and the oxygen the same in this container? Is the pressure of the nitrogen and the oxygen the same in this container? This is a simple, these would be like multiple choice type of questions. The nitrogen and oxygen have the same pressure, true or false? But you'd say maybe that question's not phrased in the best manner. What would you want to know? True or false? You would have to say what? Is the nitrogen and oxygen the same pressure in this container? You would have to say false, because it might be, it might not be. We don't know, because it depends on
which rule you're using.
Yeah, exactly. Which perspective you're using. And so, how about this? Is the volume of nitrogen and oxygen the same in this container? Is it possible that's true? It's obvious. It's got to be true, because it's in the same container, right? But is it always true? No. And so those are the things that that take time. It's this type of stuff you don't learn like the night before the test, right? This type of stuff, you let it sink in, and you usually have to work at it. Most of those things that you're going to encounter as you progress in science are things that don't click the first time you hear it. If it clicks, then it's been simplified quite a lot. But you go to most scientific conferences, and these are people who've been spending 20 years on this, or or grad students who've been spending a good proportion of their life dealing with this. And so somebody who's spending their life, you aren't going to have the same understanding, are you? And you don't expect to have the same understanding either. You expect to get it in little bits and pieces. Well, the same thing with this. It's not that difficult. It's just, a lot of people don't think about it, and they continue not to think about it, and then the exam comes and they still don't think about it. And so this is something you got to think about. And then we're going to come to the next series. Are the nitrogen and oxygen molecules moving the same speed? Do the nitrogen and oxygens have the same average kinetic energy? Do the nitrogen and oxygen molecules have the same temperature? They got to have the same temperature. It's the same. It's air, right? We must have the same temperature. It's impossible to have separate temperatures for that. But are they moving at the same speed? Well, maybe you can pick one nitrogen molecule in there and another oxygen, and they have pretty much the same speed, but that would be coincidental because the average, although we don't really use the average speed, what do we use instead of the average speed? We use the RMS speed, and the RMS speed is called, what does RMS stand for? Root mean square speed. And so are they going to have the same root mean square speed, the oxygen and the nitrogens? Yes or no? Let me tell you, since the average kinetic energies are the same for oxygen and nitrogen, then the speeds, the RMS speeds must be the same. True or false? True or false? False, good. False, because, you know, even though their energies might be the same, it's like mass is very important. In physics you learn, you know, for a big truck, let's say you have a semi-truck moving at some energy versus a small compact car moving at the same energy. You know, are they both going to be moving at the same speed? No way. You know, the small compact car has got to be moving much, much faster because of its much lighter mass in order for the two energies to be the same. And so these are things you want to review and ask yourself. You know, do you understand gas mixtures? Yes or no? If you understand gas mixtures, then you can quiz yourself appropriately. And these would be the questions you'd ask yourself, okay? I think you probably need more time to digest it, right? Maybe, because I didn't hear rapid answers. But once you have it down, then those are very easy questions to answer, you know, quickly and confidently. How you do it is you just go over it, you know, once or twice or 3 times, or however many times it takes. Well, how can I calculate the speed? Now, these equations you don't have to memorize, right? These equations we can, I'm just going to give you, and you have to know how to use them. So the URMS speed can be determined in 2 different ways. One is, you know, this 3RT over the molar mass, you know, thing. Another is by rearranging this. This is one of Newton's laws. Newton, that the average kinetic energy is equal to 1/2 m u RMS squared. And so if we just solve Newton's law here, one of Newton's laws for u, then we get u RMS is equal to 2e bar k divided by m. And I'll take the square root of that. A couple of different ways we can determine that. It turns out the URMS speed is fast or slow at room temperature? Fast, incredibly fast, right? These molecules are moving at incredible high rates of speed, but you don't notice it. Well, one, you don't notice it because they're moving so fast, but they're so small. You know, the impact. And so we feel the collisions all the time. You know, these molecules colliding into us at high rates of speed. And actually 14 pounds is a lot of pressure. You know, atmospheric pressure, that atmosphere weighs a lot. You know, it doesn't seem like it, but you know how you could tell 14 pounds is a lot of pressure? How you could tell is go into a vacuum. You know what happens if you go into a vacuum? Well, I'll show you. We'll create a vacuum. Try to create a vacuum. Anyway, what else do we got? Well, we know the average kinetic energy is going to be the same between those URMS. There are other things we can calculate. You know, things like that we should know, like things like mean free path. You know, the mean free path out in space versus here on the surface of the Earth is quite a bit different. What do you think the mean free path is? Take a guess. Like in this room, what do you think the mean free path is? You know, how far does that, you know, we know that oxygen and nitrogen are traveling extremely fast, but the mean free path is how far they travel on before colliding into something on average. And so, you know, the average distance traveled before collision. There's going to be a distribution, of course, right? Sometimes short, sometimes long. But and so, any ideas? You know, we know that air is mostly empty space. And so it's mostly empty space. They must travel a long distance before they collide into something, correct? And so if we look at under ambient pressure, you know, ambient pressure is a little different, or is it? No, it's not. This is in, what is that? H pascals, millibars. This is millibars. No, H, what is H? So I don't know that one. But millibar, 1013 millibar, which is about equal to what? 1013 millibar is equal to 760 millimeters. And so what we say is a millibar is roughly equal to a millimeter. You know, it's way off, but it's close enough for us. And then well, 1.013 times 10 to the third millibars would be 1.013 bars, which would be which would equal 1.013 bars is equal to 1 atmosphere. All right, and so what we say is 1 atmosphere and 1 bar are about the same thing. Close enough. And so at ambient, we have 10 to the 19th molecules per cubic centimeter. Is that mostly empty space? It turns out, yeah. Even though that's an incredibly huge number, it's mostly empty space. But take a look at the mean free path. Did you think this was going to be the mean free path? You know, I was thinking the mean free path is going to be like this. I mean, this air is mostly empty space, so the mean free path is going to be kind of long before it hits something, right? But look at the mean free path, 68 nanometers. Is that a 68 nanometers, is that a very far distance between collisions? It's nothing, right? But from the perspective of a molecule, it's a huge distance. This is a huge distance because a molecule, about how big is a molecule? Actually, we haven't gotten to this, but does anybody know around how big a molecule is? Or how big is an atom? How big is an atom in meters? A nano is what? 10 to the minus?
12.
Nanometer.
Or 9.
Nanometer is 10 to the minus, well, a micro is 10 to the minus 6, so a nano must be 10 to the minus 9. Atoms are about 10 to the minus that's an awfully short mean free path because atoms are roughly 10 to the minus 10 meters. 10 to the minus 10 meters is an angstrom. You know, 10 to the minus 10 meters. And so this mean free path is short. I thought it was longer, but according to Wikipedia here, it's pretty short. Well, if we go to low vacuum is considered anything from 1 millibar to 300 millibars, you know? And so we're looking at like, you know, a couple of hundred millimeters of mercury. You know, a couple of hundred millimeters of mercury still, you got some air in there, but not much. And look, take a look at what happens to the mean free path up to microns now, 100 microns. Medium vacuum is 10 to the minus 3. You know, 10 to the minus 3 would be, you know, what we call millitorr. You know, normally when we're thinking about vacuum, millitorr is a unit that's frequently used. Millitorr vacuums aren't too hard to get. You know, you don't need too much of a highly specialized equipment, but when you get to high vacuum, ultra high vacuum, these are very difficult to get. And in fact, for ultra high vacuum, you have to use stuff that looks like a submarine, you know, very thick walled stainless steel, everything sealed with gaskets and welded, and still you have vacuum leaks. But when you get to, let's say, high and ultra high vacuum, at ultra high vacuum, look at the mean free path, 10 to the 5th kilometers, you know, at 10 to the minus 12. It's very hard to get, but is that seeing very many molecules? Not at all. And so mean free path, this is something we can calculate, but we aren't going to calculate in this class, but from kinetic molecular theory we can get this. If we know the mean free path, or we know how many molecules per cubic centimeter or how many molecules per cubic meter, we can also get something called the collision frequency. And so how frequently do collisions occur, you know, between these molecules? I know in the primer it said they collide infrequently, but do you think that's the case when the mean free path is only nanometers in distance, 68 nanometers? In distance. This article needs attention, so unfortunately this one is not, collision frequency is not on, updated on Wikipedia here. Let's go to Google. Collision frequency, take a look at that. Oh, Davis. That's probably not what I want to search. I want to search collision frequency in air. The Chem wiki on Davis is actually pretty good. I don't have the numbers memorized, but what do you think? Extremely huge or what? Oh, this is interesting. Okay, do you see molecules of diameter, what, 10 to the minus 10 meters? 10 to the minus 10 meters is called an angstrom, right? Angstrom is a very common unit for chemists. And so it usually varies from 1 to 5 angstroms. We'll go with 5 angstroms with that, although oxygen's not. We'll go with something like 3 angstroms. Oh, molecules, molecule, we'll go with 5 angstroms. Molecular mass of 28, or, you know, molecular mass versus molar mass are two different things. Okay. Wow, this does all the calculations for us. Average molecular speed, 474.6981 meters per second. Although, you know, my diameter of the molecule is going to mean these calculations are going to be off. The mean time between collisions is 10 to the minus 10 seconds. The collision frequency is, take a look at this collision frequency, 1.3 times 10 to the 10th collisions per second. How many, that's 13 billion collisions per second. Is that infrequent collisions? I don't know why they're calling it infrequent collisions, but you know, to me that's a lot of collisions. 13 billion a second in air. Well, anyway, this is kinetic molecular theory. These are the types of things that we want to know about this mixture, right? Or a gas. It doesn't have to be a mixture. It could be a pure gas sample as well. types of things. All right, but this is a kinetic molecular theory of an ideal gas. Ideal gas, why ideal? Because it simplifies the math tremendously. Because when we're thinking about an ideal gas is just a point in space, right? This is a particle. And this point in space doesn't vibrate, it doesn't rotate, it doesn't do those things. If we have to add vibrations and we have to add rotations to the kinetic energy, then all of a sudden these equations get much, much more complicated. And so the simple thing is just ignore those and treat these as ideal gases. But the problem is if we treat everything as ideal, then sometimes we're going to get errors. Right? And so let me give you an example of this here. Let's take a look at two gas molecules, and I calculate the volume. And so the next example is ideal versus real gases. Ideal versus real. Well, do you recall what makes an ideal gas ideal? There's two things that make an ideal gas ideal, two things that we ignore that simplifies the equations. They simplify the equations so that we have one equation that describes the gas, at least the physical components of the gas. Ideal. Ideal means two things. One, the volume of the gas particle is 0. If you go to Charles' law, you know what Charles' law is? Charles' law is this volume versus the temperature deal. You don't have to know it's Charles' law, but you know what happens is the temperature goes to 0 Kelvin. The volume decreases. And when you get to 0 Kelvin, the volume of the gas should be 0. But is that possible? You know, the volume of an ideal gas at 0 Kelvin is 0. And so the volume of a gas at 0 Kelvin is 0. In other words, exactly 0. Is that true? No. It's not true because the gases are made up